Every single second, our modern enterprise networks must absorb a truly staggering influx of continuous, raw digital information. Devices like the Ray-Ban Meta smart glasses operate as continuous, ambient data collectors, constantly streaming environmental metrics rather than simply recording occasional video. For decades, the standard procedure has been to route all this raw data back to massive, centralized cloud data centers for processing. This architecture concentrates data processing within the infrastructure of a few major providers, making the entire network dependent on their specific hardware and software stacks. It also creates physical vulnerabilities. If the dual inlet fiber optic cables entering a major data center are severed, the entire regional network goes dark. To prevent these localized collapses, we have to process the data locally, exactly where it is generated. This is edge computing. You cannot simply copy and paste an entire data center into a retail store or a factory floor using traditional hardware. We have to completely decouple the network's functions from the physical boxes. Processing at the edge is a strict necessity, dictated by the unforgiving laws of physics and network latency. Historically, corporate networks relied on highly specialized hardware appliances. If you needed a deep packet inspector, a firewall, or a content delivery network, you bought a specific proprietary box engineered to do exactly that one job. Deploying these proprietary boxes at the edge means buying, shipping, and maintaining thousands of distinct physical units. The spatial and financial costs make outward scaling impossible. Inside specialized appliances, the architecture is simple: a standard CPU, memory, storage, and ports. This drives network function virtualization, or NFV, physically separating hardware from software. Instead of a proprietary box, you deploy a generic server running the firewall as a software virtual machine. This reduces all edge hardware requirements to 3 basic archetypes: servers prioritized for heavy compute, for heavy storage, or heavy network routing. A standard server running firewall software performs the same role as a specialized appliance, meaning network capabilities are no longer tied to proprietary hardware manufacturers. This abstraction of hardware logically expands into software-defined networking. Consider a physical switch wired to 4 light bulbs. Hardware allows one action, turning current on or off. Insert a software layer, and it sends a binary signal instead. The software translates this into code, allowing endless binary combinations and patterns without altering a single wire. When you scale this logic from 4 light bulbs up to massive enterprise routing protocols, the operational limits of a physical network disappear. In a software-defined system, the hardware acts only as a dumb executor. The software layer entirely dictates the physical reality and capabilities of the network. Network functions now exist as lightweight virtual machines distributed into 3 geographic tiers. First, the cloudlet, on-site data centers for an enterprise. Second, fog computing, compute power embedded inside transit routers. Third, mobile edge computing, or MEC, micro data centers positioned at the cellular boundary. In practice, MEC nodes are containerized servers installed directly at the base of telecommunication towers, processing data before it ever hits the broader internet. The physical distribution of these nodes follows a specific topographical taxonomy, organized by the technical requirements of the organizations that deploy them. To test this architecture, we look at the ultimate strain on any network: continuous video surveillance analytics. If a city attempts to stream raw 4K video from thousands of security cameras back to a central cloud, the data pipeline immediately chokes, the bandwidth saturates, and the latency renders real-time analysis impossible. Now, place a mobile edge computing node at the local cell tower to intercept that raw 4K video. Instead of uploading the footage, the edge node runs deep learning inference locally, scanning the massive video file frame by frame for a specific target, like a suspect's vehicle. When it finds the match, the node extracts a microscopic metadata payload, just the license plate text string and a timestamp. It then discards the heavy video file completely. That tiny string of text slides effortlessly up the pipeline to the central database, arriving in milliseconds with near zero bandwidth cost. Edge processing converts bandwidth-heavy raw observation into microscopic, highly actionable intelligence before it ever burdens the macro network. Because this metadata is incredibly light, Centralized clouds can now track isolated targets across infinite decentralized edge nodes in real time. This capability provides high-fidelity oversight for the network, while simultaneously eroding individual privacy. The deployment of these MEC microdata centers is currently moving far faster than regulatory frameworks like GDPR can adapt. We now face the unresolved question of how to govern an infrastructure capable of processing, analyzing, and discarding reality at the local level without centralized oversight. As edge infrastructure evolves to process data locally, the technical requirements for network security increasingly conflict with existing legal protections for personal privacy.